This is the video podcast for Chapter 16 on lumped hydrological modeling. And before I get into that, first I want to congratulate you because you've made it through the first 3/4 of the class, so we're most of the way done. And what I've tried to do is I've tried to use the first 3/4 to go through different parts of the landscape, whether it was forests, rangelands, urban areas, wetlands, floodplains, and look at the water balance in each of those contexts. In some cases where you have more dynamic landscapes, we've looked at the hydrogeomorphic processes that are there, and we've always looked at the interaction between hydrology and plants in the areas that we're looking at. So we've treated the landscape as being composed of individual patches and thinking of these patches as each functioning differently. What we're going to do now is totally switch gears. Instead of thinking of each part of the landscape as really its own basic building block that has its own unique set of functions, we're going to say, well, what if we treat the whole landscape as one integrated system? This has some advantages and some disadvantages, but I want to introduce you to the ideas of how we go about that conceptually and quantitatively. So we have this term lumped hydrological modeling, and it means to treat the watershed as one whole entity. We can consider it lumped in the sense it's just basically one thing, and we're going to look at what goes into it and what comes out of it. But before we do that, I would like to present a little bit of an overview to frame the next set of lectures here in this unit, just to give you a sense of how this fits into the larger path that you're on in your career. So part one here is going to talk about land use planning and what a model is, and essentially how you would use that in your career. And then part two will be a separate podcast that will go into the nuts and bolts of this first type of hydrological modeling. I want to look at overall land use planning because it's important to understand that hydrology is an integral part of managing the land. On a regular basis, it's something that has to be accounted for, and people, cities, planners of one kind or another, county managers are all considering this more or less. But what we want to do and what I want to train you to do is to make this a more transparent and equitable part of the work that you do in your career, because this is one of the things that if you don't pay attention to it, it can really turn around and bite you. And we see that with major floods or droughts or forest fires, other disturbances, as well as outbreaks of GI viruses, cryptosporidium or things like that. We see in society that things happen that the technocrats who run things were not really prepared for. And of course, if the technocrats don't have it, then that the politically appointed democratic leaders are not in a position to deal with it either. So, within this context, I want to introduce you to the idea of 4 different kinds of land use planning. The first is the most simple. It's the most commonly used approach that I see out there, which is extrapolation. It's the same way that we manage our money, and why not manage our land that way? And that is to say, how have things been recently? And let's just keep managing the land as if it's going to continue as it is. So whatever data you have, you just take those past trends, like, well, here's the water use that we've had, here's the supply, here's the demand, and just project those into the future. And that will work okay in the short term, but of course, the history of civilization in which large unexpected events take place, whether they're natural events or societal ones, and as a result of that, extrapolation always fails at some point. Another approach is reaction to crisis. And of course, this often goes hand in hand with extrapolation. Now, it's inevitable that humans are going to get into crises. That's part of how it goes. But in many cases, systems are run, planning is run with actually very little forethought and planning. Like the decision gets made, we're going to take a relaxed attitude and let things unfold because that's the lowest cost solution. So let's just let the free market work. Let's not do a whole lot of activity, and we'll just sit back. And then when the crisis comes, then of course something has to get done. And so then at that point, what ends up happening is it costs disproportionately more money to solve the problem than it would have taken had more been invested in planning and preventing the problems in the first place. And then even still, what the actions that get taken often don't address the root problems of the crisis. Sometimes the crises are not actually physical. They might actually be manipulated in economic or political terms, and so then that doesn't get accounted for. Conversely, they might be such long-term environmental or water problems that no quick political fix can actually deal with the crisis. Another thing that you see, and we see this a lot here in California, is an engineering-based approach called systems analysis. What you try to do here is simplify a system down to its core elements and then make a model that tries to come up with the optimal solution for that. I know this kind of falls in the direction of game theory and mathematics, but it has its own branch in engineering called systems analysis. And a classic example would be, okay, here's a map of all of the roads in my county, and I'm in a county that snows a lot. So I've got 30 snow plows and 1,000 miles of roads. How can I get all those snow plows to cover all of the roads, once a day or once a week or whatever, in the least amount of money with the least amount of repetition? So what you do is you specify what your system is, and then you start adding constraints. I want to do this. I want to minimize that. Kind of like when you ran Solver in some of the early assignments. And so basically by taking this approach, you can come up with whatever is the one optimal solution, or you can come up with a range of trade-offs. If you want to do this, you get these choices. If you want to prefer that, you get these range of choices. So this is an approach that's good when systems are relatively simple, like snow plows and roads. But when you're talking about hydrological systems, it's far more complex. And this is an approach that is used. The advocates of this approach say that by using an approach that's simple, they can create a lot of transparency. Detractors would say that by missing all the important details, there are key aspects of the system that don't get accounted for, and the system may not be so simple. And then lastly, there's a more hands-on, time-involved approach that would be landscape-based planning. We see this in a lot of places. The European Water Framework would be one. Here in California, we see these regional water management groups or watershed management. I can't remember the exact acronym, but it's like regional water management planning, something like that. Where you try to get everybody involved in a collaborative process to try to characterize what are the functions in the landscape. What are the societal needs for those, from the landscape in terms of land use and water needs, and then trying to create the right blend of naturalization and societal infrastructure to meet as much of that as you can. Now, in order to do this, you have to do a lot of science and legwork to characterize what's going on. And to do that, it's very common to pick the watershed as the central organizing element, because this is, water and water-related things tend to not cross those divides. Now, vegetation does, air and air pollution does, but from a management perspective, it's a really good choice to look at water management from the perspective of a watershed. So the key, again, is to characterize those functions. And so what I've been teaching you in this course is to look at the different patches in the landscape and try to understand what the ecological functions are, what are the hydrological, the water balance, the hydrodynamic processes, the geomorphic geological context of the system, and then put all that together to come up with a plan that addresses those concerns at the same time as working on societal needs. In all those approaches, there's always a place to have a model of some kind. And so it's worthwhile to spend a little time reviewing what a model is, or introducing you to what a model is, and talking about the different types of models that are commonly used. A model is nothing more than a representation of a system to try to understand its behavior better, to just be able to play with it like a sandbox, but then also to be able to predict its behavior to, have a better understanding for the future. The simple diagram here on the slide just tries to summarize it. The model itself is often like a box or black box. Some people might think of it if they don't know what's on the inside. And the model is an operator. It takes some inputs, it does something to them, and it produces outputs. Usually the inputs are going to be whatever the drivers are of the processes, and the outputs are going to be water balances or fluxes. It could be growth of trees. It could be prediction of landslides, and whatever the environmental system is that you're interested in predicting. In terms of the types of models that we see in hydrology, there's a range of types, and I'll just work through those. One type of model are called scaled or physical models. This is where you try to rebuild the system smaller than its actual occurrence and then play with it. It's the sandbox approach. I mean, look at this image on the right. Here is a empty reservoir, the Glines Canyon Dam Reservoir, and you can't see it on the picture, but there's a dam. And the idea here is if you take that dam down, what's going to happen? So they're feeding sediment and water in. There's a delta that was there from when the reservoir was present, and they're learning about how does sediment and water behave when you remove a dam. And in fact, this dam has now been removed. It took 25 years of study and physical modeling and a whole host of analyses to get to that point. But these types of models are very useful. The San Francisco Bay model, it has been long used to try to understand water and salt balance issues in San Francisco Bay. So if you were going to dredge or cut a new channel, how would that affect the flows in the system? Another type of model, which was essentially intended to save money compared to having to create a physical model, is an analog model. So with an analog model, you're recognizing that the flow of electricity works the same in terms of the math for flow of water. Electricity flows along gradients and water flows along gradients. So you can create circuits that would have that same capability. And so, here's just an image. I don't expect you to fully understand or, know this for an exam, but, a case where you have a coupled tank flow system and then how that can be done in an electrical circuit to represent that system. Overall, though, mathematical models have come to the fore as very powerful and flexible tools that can be used in science and management. I think physical models are still overlooked and should be used more than they are. But mathematical models can be done by almost anybody just with a desktop computer. It's become highly accessible with tremendous opportunities, and so it's important to really understand them. In a mathematical model, you have some kind of equations that are describing the behavior of a real system, again, where you're trying to say, well, what's important out of the system, and then model that. There's all different kinds of ways of doing that. And so, this is a diagram that illustrates from a watershed perspective, what are the two main pathways of going about this. And it's really interesting, like, when you think about hydrology, you don't think, what are the grand debates in civilization and science? But in fact, we have some, and one of them is right here. Is the world fundamentally random, or is it fundamentally ordered? That's the most basic thing you can ask in science. Of course, I gave you an assignment to play with your wetland data and see if high tides were random or not. And this thing comes to in models, because we can make models using equations of randomness, or we can make models using equations that are predicting specific functions. So for random systems, we use what we call stochastic models. Stochastic just means probability based, and assuming that a system is random. Deterministic means that something is governed by ordered laws, like natural laws, and we can divine what those are. We don't really worry about where the laws come from. That's not important here. But just that we can use those equations to actually predict the future. For example, if you got in a car and turned the key and it didn't work, then you would know that the ideas embedded in the models of how cars work are wrong. But the fact that a car does work, we have combustion, and the car drives, means that a lot of that is actually deterministic. Within deterministic models, we can look at them in terms of treating the system as one entity, what we call lumped, or we can treat it as distributed, which means breaking it up into lots of small pieces and then looking at each piece independently and then aggregating up. We can also treat flow as constant, so we use the term steady to mean just constant flow, or transient. And of course for hydrology, transient is the norm, right? It rains, the rain stops. The flow rises and falls, so that's transient flow. On the stochastic side, we can treat the randomness as just not only random in time, but random in space. Or you can consider it as having some sort of structure in space or time, and so those are the choices on that side. Okay, well, let's look at some of the different ways conceptually that this can play out. I'm going to give you some relatively simple examples of these different types of models. So the simplest form of stochastic model is something you could easily do yourself. You just collect observational data, whether it's, whatever kind of data you have, just get a time series of it, and then start by assuming that each point in that time series is independent and part of the identical distribution of a population from which those samples are taken. When you do that, you can then create a histogram. If you have Excel or something else, a histogram, is a representation of the probability distribution of the samples you have, which is supposed to be representative of the probability distribution of the population. You can then calculate the metrics for that distribution, and then you can use a random number generator to create new numbers that have the same distribution, but then they aren't necessarily ordered in space and time. And so, for example, in the left plot here, I show stream flow ranging from like 600 to 1300 CFS. And then I take the real data, which is the black data here, get its distribution. I've got the mean and the standard deviation. It fits a bell curve pretty well. So I use the normal distribution, generate random numbers with the same mean and standard deviation. The open bars here with the dots are the future as you predict stochastically, and you can see that they match the same distribution. Here's the actual time series of that. It was like, let's say 100 days worth of data or something. And then I just take the stochastically generated numbers and put them in a sequence here, and I get a representation of what could happen. Stochastic models are not, in this case, it's not producing a temporal order because each point is thought to be independent and identically distributed. So you're just generating one sequence here, just in the order that the random number generator produces those numbers. And that would be a stochastic model with a prediction. And the prediction matches the distribution, and therefore it would be seen as viewed as an excellent, accurate prediction. Well, there have been people who are highly critical of this approach, as there are of any approach, but this is just too fun to pass up. There was a hydrologist named Vit Clemis, and he had this to say about this, so I'll just read this because I just love it too much. But similarly devoid of hydrologic content has become statistical hydrology. 10 years after I made this assertion, an opportunity presented itself to test its validity. When a leading American flood frequency analysis (FFA) expert, that's a stochastic modeler, asked me for a set of flood peak discharge data, so real data, to test his new regional flood frequency model, and explicitly requested that I give him no other information except the numbers themselves. So I sent him a set of fabricated numbers from which his model duly produced the required regional flood distribution. Since I still have the computer printout with the results in my files, I can tell you with confidence that, for example, the 10,000-year flood for the region is 2.5181. While the units are not known, as requested I supplied only numbers, the magnitude of the flood must be quite accurate because the parameters of the distributional model are given to 8 decimal places. To the credit of the investigator, I must say that he detected some peculiarities in my data, namely that some of the computed model parameters pointed to a small homogeneous region, others to a large heterogeneous region. I assured my friend he was right on both counts. The small region was my desk, the large region my imagination. So of course, anytime you're working with data, you have to think about it. You have to be critical. As I've said before, the things that may make person a little bit spicy and not so nicey are the things that make them a great skeptical scientist. So that's what Vid is calling for here, as I read it, is basically saying, you can use stochastical modeling, that's fine, but just be mindful of what you're producing and whether that's realistic and meaningful. Okay, on the deterministic side, one type of deterministic model is empirical. Now, empirical models do use statistics, but they're attempting to use statistics not to get at probability distributions, but to get at underlying natural laws. So this is a case where you collect observational data just as before, but instead of coming up with a random set of predictions, you try to predict it based on some other variable, and we typically use a regression. I know most of you are familiar with regressions. So a regression is typically assumed to be valid over the range for which you have data if you go through all of the processes of testing the assumptions of those models. So are the residuals normally distributed and meet the criteria of homoscedasticity and all things like that. So as an example, let's say you were to collect rainfall and streamflow data. You fit your regression, and we get the regression equation. Usually we're going to test this also for the coefficient of determination and the p-value, which tells us the likelihood that this is generated by random noise. In this case, you can see that these blue dots represent a very strong fit, so let's not worry about that detail. So in terms of time, you have the streamflow series here. Now, in order for this to work, you want to make a prediction in the future about stream flow, but since that prediction is going to be based on rainfall, you have to first know something about the rainfall in the future, which means you would need a weather forecasting model or a climate forecasting model. If you had that, then you could use an empirical equation such as the one shown to predict the future stream flow on the basis of the future expected precipitation. Analytical, also known as theoretical models, these are ones where you can write out an equation and it doesn't require any like parameterization or just it doesn't require, like, the equations are just pure, they're just pure math. You solve the math and you get the answer. And we do have that capability. A lot of things in nature are governed by error, well, I don't want to say distributions, but the same functions that are governed by the normal distribution, which is called the error function. We can get direct analytical solutions to things like the diffusion equation. Think about basic physics, pendulums, waves, conduction. These are things that we have very good predictive equations for. So for example, you could have a purely theoretical model that would predict stream flow. This is going to have an input, something like precipitation. It's like you might have a function, y is a function of x is going to be precipitation, y is going to be stream flow. This is a plot through time that shows observed data in blue, predictions in red, and you can see how the wiggles roughly match, but there are times when they don't. And then you can look at the predicted versus observed scatter plot and see if you think that that is an accurate model. Okay, the last type of model is the full-blown numerical model. This is a case where the equations themselves or the input functions and boundary conditions to go with that are simply too complex to solve with pure analytics. You have to actually come up with numerical approximations through brute force computation. Typically, these numerical models are going to be using some combination of mass, momentum, and energy, but sometimes just one, sometimes combinations. It may have any level of difficulty. They could be nonlinear or linear. They could be ordinary or partial differential equations. But it's going to be using a brute force approximation to compute it. So some examples of a numerical model would be what's shown on the left, which we're going to talk more about in future lectures, where you take the three-dimensional structure of a watershed and you discretize it into volume pixels, what we could call voxels, and you're going to solve a water balance for each voxel, and you're going to then pass water through from voxel to voxel and then come out with what are the water balance terms. Another example might be a two-dimensional situation where you're not worried about the vertical dimension, but just taking advantage of the topography and aspects of the surface. Then you can calculate, whether it's a water balance or as shown here, and a soil erosion risk map. And then the last thing is that any type of model, you can ask this list of questions. And if you can answer all of these questions, then you understand what the model is. So does the model attempt to replicate reality precisely? In other words, is it a prediction model, or does it merely simulate possibilities for the purpose of scientific exploration? Now, why would anyone build a model that isn't a predictive model? Well, there's a lot of good reasons for that. I mean, first of all, we have systems that we can't predict very well. We may not know all of the functions or how they might interact. And so you might want to make simplified scenarios and try different trade-offs to see what works best. Does the model attempt to include all possible processes or extract just the most significant ones? Again, though, this is how models are user selectable. We create them and how we program them, and so therefore we can get them to do whatever we want. And there's a lot of human choice that goes into how a model is going to perform. Is the model spatially aggregate or explicit? So that's the lumped versus distributed. You're going to be learning a lot about that in this next unit. Is the model for one event, or does it track flow through time? We'll see more examples of those differences. Does the model focus on a single scale and extrapolate, or does it somehow consider different scale-specific processes? So for considering a single scale, that could be a lumped model. It could be cellular-based, like voxel-based approach, but where each voxel can only have a certain size. Some models allow, instead of using, like cube voxels, they might be volumetric, but they might have any arbitrary shape. And so they might actually have, you could also write in different equations for different spatial scales. Is the model steady state or temporally dynamic? So that's, again, is the flow just constant, or does it vary through time? And then is the model oriented towards understanding watershed processes, or is it more of a resource tool where they don't really care how it functions, they just want the right answer to come out of it? So I'll stop there. I've tried to give you an introduction to think about the overall approaches to manage the landscape, and then regardless of what approach, it's possible to draw on a model as a tool to help. And these are the different kinds of stochastic and deterministic models that are available.